So any information about the internals given to you? Second internals?
First week of July.
Yes. First week of July. Who told you, Azim? How did you get that information?
Max ma'am told.
Vignesh sir. Okay. So lot many of people, around 40 people did not submit your assignment, which was given to you as a classwork for every class. I told you to draw the diagram and submit. So only 21 people have given that. Why? What is the reason? Yes, what is the reason for that? So within end of today's class, I want everyone to submit it today evening. Is that fine? Yes. Are you able to hear me, guys?
Yes, sir.
Okay, so within today, everyone should submit the pending classwork. Okay. Fine. So in the last class, we were discussing about the regeneration. So how the regeneration helps us to increase the efficiency of the steam turbine, which is running on a Rankine cycle. So we were discussing in the last class. What we used to do is we used to take some amount of steam intermediate of the expansion. Between the expansion, we will take some amount of steam and we will send it back to heat the water which is coming from the condenser. This is how we were able to achieve the regeneration in case of the Rankine cycle. So any doubts in that regeneration part?
No, sir.
So today we'll be discussing about the reheating. Reheating is very easy. You already learned in the Brayton cycle. Similar application would be there in case of the Rankine cycle. So intercooling, the concept was there. Intercooler is something where you incorporate it between two compressors. So as there is no compressor, do you have a compressor in a Rankine cycle or a steam turbine? Do you have a compressor?
No.
So we don't have a compressor, rather we have a pump here. So that particular pump helps us to increase the pressure from 3 to 4. So basically what we are doing is we are getting rid of intercooling. So as compressors is not used, intercooling cannot be offered. So, but the turbine is being used to expand the things and get the work output. So if the turbine is used, there is a chance of usage of reheater. Yes or no? So you can make two different turbines, or you can expand in two different stages. First in high pressure stage, later in low pressure stage. In between, you can add still more amount of heat to the system. Getting it? It is similar to that of the Breton cycle. Breton cycle, what was happening? Once the expansion was done, again you are heating it, again you are sending it to the another turbine. Correct? So similar thing would be carrying out here. Okay. Can you guess the TS diagram of this? Are you able to understand it? Are you able to understand this? So 3 to 4 is what, anyone? What is 3 to 4? Anyone? 3 to 4. What happens?
So pumping is done, so water.
Pumping is done. So this is the pumping work where you increase the pressure value. So once 3 to 4 pumping is done, 4 to A to B, and B to 1 are the heat addition processes applied in three different phases in three different equipments. So 4 to A is what?
Economizer.
Economizer. What you are heat? Yes, what you are heating here? Whether you are heating liquid, liquid plus vapor, or vapor.
Liquid.
Liquid,
Liquid,
liquid.
isn't it? So here the temperature increases or the phase changes. What happens here?
Temperature increases.
What about the phase?
It remains same.
Very good. So now A to B. A to B, what happens? Where it happens? A to B, heat addition.
Boiler.
Boiler,
Boiler.
heat addition happens. So whether the
Phase change.
temperature is increased here?
No, no.
No temperature increase. The phase will keep on increasing from liquid to vapor. So the phase will continuously increase from liquid to vapor. There's a transformation in phase from liquid region to vapor region. Okay. So at this particular point, at the point number B, you have complete vapor which is transformed. Now again, if you heat it in a separate equipment, what happens to the temperature?
Increases.
Temperature increases. There is no more phase change here. So B to 1 happens in which region? I mean, which equipment? B to 1. So it happens in a superheater. Now, once the superheating is done, you'll go and hit the turbine at state 1, which is high temperature, high pressure steam will impinge on the turbine so that the expansion happens. So expansion happens from 1 to 5. Okay, not completely up to 2 here. You are not going completely up to 2 because of the reheating. You are just making it 1 to 5. So once it has reached 5 or it has reached nearer to the vapor phase, again what you're doing it? Again you're heating it back to the initial state, initial pressure. You're heating it back to the initial pressure. How you are heating this? Which equipment are you using for heating
Reheater.
back? Exactly. So you're using a reheater to heat it back to the initial pressure and initial temperature. Okay. So now once you're heating it, what happens? You will send the steam once again to LP turbine where it completely gets expanded and transforms itself into a liquid plus vapor mixture. So now it is liquid plus vapor mixture here. Here it was complete vapor, which was in superheated condition. At the end of expansion, what happened? It get transformed into liquid plus vapor. So from this, you will use a condenser to eject heat from it so that your liquid plus vapor will gradually condense itself into a saturated liquid at state 3. At state 3. This saturated liquid again is being pumped back into the system at state 4. Again, it goes on into economizer and the cycle repeats. Any doubts in the reheating one? Any doubts in the reheating? Any doubts?
No, sir.
Good. Okay. So let us try to calculate efficiency now of the reheat cycle. Okay. So how will you calculate efficiency? Efficiency is nothing but output divided by input. Now, output in the sense it is work output divided by heat input. Work output in the sense is equal to the total work output is equal to total heat interaction. Work interaction is equals to heat interaction totally, which is according to the first law, divided by QS. So total heat supply or total heat interaction, what it is. How many heat interactions are there? Kiev 4 to 1 is there, correct? Yes or no?
Yes, sir.
Yes, sir.
What is another heat interaction here?
Q 5 to 6.
Q 5 to 6 is another heat interaction. Next, one more. One more heat interaction. Q4 to 1 is you're supplying heat. Q5 to 6 you are supplying heat in case of a reheater. Where you are going to eject heat, that is also a heat interaction. Where you are ejecting the heat. Yes.
Q 6 to 2.
Q 6 to 2. 6 to 2 is what? What is 6 to 2?
Work output.
So where you are going to eject the heat?
1 to 5.
1 to 5. 1 to 5 is what? 1 to 5 is expansion in the turbine. This is high pressure turbine. Again you are reheating it from 5 to 6. After then again you are getting it expanded from 6 to 2 in a low pressure turbine. So 1 to 5 and 6 to 2 are the expansion processes.
3 to
I
2,
said
sir.
it is 3 to 2 or 2 to
2
3.
to 3. 2 to 3.
1 to 3.
So 2 to 3 is the region where you are giving out heat so that your liquid plus vapor mixture would gradually condense into complete liquid. Your vapor will be condensed into the liquid. So this is the condensation process where you are ejecting the heat. So that I'll be taking it as Q 2 to 3. Okay, divided by. So heat supplied, where you are going to supply the heat here. Heat is supplied where and where?
4 to 1.
So Q 4 to 1, you are supplying heat plus
5 to 6.
Q 5 to 6, you are supplying the heat. So this forms the complete expression for the heat engine. Now I have to define what is Q4 to 1. I have to define what is 5 to 6. And what is 2 to 3. Can anyone say me how do I calculate this three things? Either you can calculate in terms of T into delta S. So Q can be calculated in these terms, guys. First, Q can be calculated as T into delta S. That is one type of calculating heat. Second, Q can be calculated in difference of enthalpy. That is also that. Q can be calculated in difference of enthalpy. And third one, which you have learned in the previous chapter, even Q can be calculated as MCP delta T. That also can be done. Okay, so let us see in this textbook what he has done. He has gone with the enthalpy So can you give the values of enthalpy in terms of enthalpy, heat lost in heat interactions in terms of enthalpy here? Okay, 4 to 1. How will you calculate in terms of enthalpy? Sure. How will you calculate Q4 to 1?
H1 minus
Yes.
Di-
H1 minus
Yes. How will you calculate enthalpy? It is H1 minus of H4. For heat, it is final minus initial. So final state is 1 and initial was 4. It is H1 minus H4. Next, Q5 to 6. Q5 to 6.
H6 minus H5.
It is H6 minus of H5. Very good. Q2 to 3.
H3 minus H2.
3 minutes H2.
It is H3 minus of H2. If I substitute these values over here, 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 and here, I will get the final expression to calculate your efficiency of Rankine cycle in the reheating condition. So the same thing he has done here. Okay. Is that clear? Any doubt here? So H3 minus of H2, he has just changed the signs. Okay. He has taken it H2 minus of H3 in the next step and incorporated a minus sign in between to compensate it. Okay. So any doubts here? Any doubts in deriving the expression for efficiency in case of a reheat Rankine cycle? Any doubts?
No, sir.
no,
Okay.
sir.
So yes, turbine work output you can calculate. Yeah. Again, do I require to revise this? Okay, I will be revising here. Now, anyone in this class so can give me the expression to calculate the turbine work output in HP turbine and turbine work output in an LP turbine. First HP turbine. So who will give me the expression in terms of enthalpy to calculate the work done in case of an HP turbine? Yes? Anyone? Hey, how will you calculate work done in case of an HP turbine which is 1 to 5?
H1 minus H1.
For work it is initial minus final, so that's why it is H1 minus H5. Now, how will you calculate work done in case of an LP turbine which is 62?
H6 minus H2.
It is H6 minus of H5. Very good. Now, how will you calculate the pumping work which is used to raise the pressure from 3 to 4? Work it is initial minus final. Yes, what is an expression?
3 minus H4.
H3 minus of H4. That's it. Okay. So that is what he is given here. Clear? Now, next, I guess you have learned all this in your pure substance chapter. So I have just written it so that you can quickly revise everything. So first we shall speak about the enthalpy. So I please revise this. Now I'll ask each and every person to give me the formula. Okay. So how do you calculate your enthalpy in the different regions? Suppose if it is on the saturated liquid line. So if my state point is on the saturated liquid line, your value of H1, that means H at that particular state, would be HF. Okay. Now, what if it is in the wet region? So if my state point is in the wet region, how will you calculate your enthalpy? It is HF plus X into HFG, or it is HG minus HF. So HFG is nothing but what? It is Hg minus of HF. So both the things you can understand. Now, what if my state point is on the saturated vapor line here? If it is on the saturated vapor line, it is H1, which is equal to directly the value of Hg. Okay. Now, what if my state point is in the superheated region? That means it is completely vapor, but it is superheated. So, in that case, how it will do? You have two options. Either you can use this particular formula which says H1 is equals to Hg plus Cp into T1 minus of Ts. This is not T5, this is Ts, which is superheated temperature. Or what you can do is you can directly take the value from the superheated steam tables, which I have taught you in the PTD. Okay, based on the particular value of pressure. At what pressure this particular line is there, based on that particular value, we can directly take the enthalpy value from the superheated steam tables, or you can use this particular formula to calculate your enthalpy. Is that clear? Now, same thing for the entropy, except the superheated will change. So if it is on the saturated liquid line, the value of entropy is given by SF. If it is in the wet region, the value of entropy is given by SF plus X times of SFG, or Sg minus SF. If it is a saturated vapor line, then it is Sg. Suppose if it is in a superheated state, it is Sg plus Cp times the ln of T1 divided by Ts. So this only one formula will change. So it is Sg plus Cp into ln of T1 by Ts. Or again, there is a second provision. You have to separate tables for that. You can pick the value directly from the superheated steam tables. Now, I suggest all of you to just take a screenshot and keep it with you for the reference. Okay, SFG is nothing but Hg minus HF. I told you latent heat is nothing but HFG, which is Hg minus HF. Okay, the same formulas can be followed for the calculation of specific volume if at all it is required. Taken the screenshot.
Yes, sir.
Clear now. All of you take your. How many of you have your steam tables with you? Raise your hands. Very good. Okay. 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 So anyone is having the soft copy which I have sent you in course of BTD? Anyone is having the soft copy of a steam table which I have sent while dealing with BTD, the pure substance, while I was teaching you the pure substance over there. Anyone is having the soft copy? None? In your mobile, please do check that. anyone is having a soft copy? No one?
No, sir.
Okay, no problem, dear. Okay. So I will just try to scan it and upload it into your Google Classroom by tomorrow. So you take this problem. This is our first problem in case of a Rankine cycle. We will solve this in tomorrow's class. Please do write it in your notes. Okay. Keep ready with your Steam tables. Better you have a copy with you, a hard copy that is very much required in all engineering problems. Okay. Keep that thing with you. If it is not there, anyhow, I'll be sending the soft copy. Keep your calculators ready for the next class. You're going to solve the problems. Okay. So please mark your attendance in the Google Sheet and complete the classwork which was given to you. And one more thing, guys, whoever is staying in mood with Red Town, please stay in the meeting. Rest can leave the meeting. I have to get some information from you guys. Okay. So rest can leave the meeting.